to what we're going to be talking about later in the day when we talk about more applied examples. There's not many of us here, so please feel free to stop and interrupt if I say anything that you don't understand. I'm happy to deal with any questions as we go along. So, to begin with, we're talking, when we talk about physiological computing systems, the way that I have defined these systems is that the systems where we take measures from the brain and the body and we translate them into control input at the user interface. So what we're talking about really are closed-loop control systems where we take neurophysiological measures from the brain or psychophysiological measures from the body, and they are used in order to represent the user dynamically. So these measures are being recorded all the time for the person. And what we do with these measures is that we translate them into something. This can be how hard someone is working mentally. It can be whether they are angry or whether they are tired. This is one part of the translation. And then we take that representation of a user state and we translate it again into real-time adaptation of the interface. So there are both these arrows really represent two acts of translation. One is translating the activity, the data from the brain and the body into some kind of psychological state. And the second one is where we translate that state into an appropriate action at the interface. Now, physiological computing systems and systems like them have been around for some time. You've been used, people are doing research in this area in a number of different fields. We've used measures from the brain and the body to understand how hard someone is working. This is called mental workload monitoring. And we do that with pilots, we do it with car drivers, we tend to do it with anyone who's doing safety critical performance. But we can also use the same measures to adapt technology in a more general way. So if, for example, we have a person interacting with a robot and the robot needs to respond in a way that is socially and emotionally appropriate for that person, then we could use these measures to do that. We can also use similar sorts of measures as what we call assisted technology. So John will be talking later on today about exergaming, for example, where we're trying to use this loop in order to encourage people to get exercise. The same sorts of approaches can be used for rehabilitation and those types of things. And the area of research where a lot of these things come from originally is effective computing, where since the 90s or so, people have been trying to use physiological measures to measure the emotion of the person and to get the system to react in an emotionally appropriate way. So if we have a very frustrated user, can the system detect that, and then can it do something to help the user with their level of anger or frustration? So, range of different sorts of things, and of course we're going to be talking about games today, and there's been quite a lot of work on taking measures from the brain and the body in order to make the game more exciting, or in order to challenge the player more, in order to keep the player engaged with the game. Now, this entity that we're going to be talking about a lot today, we call it closed loop control. We also call it the biocybernetic loop. This was a name first given to this concept from work that was done by Alan Pope at NASA in the 1990s. And the biocybernetic loop is a very important entity for what we will discuss today. And what I would like to do now is to go through it in a little bit more detail so you understand the different stages and you understand what the biocybernetic loop is composed of. So first of all, we collect data from the person. We can attach sensors to the head or to the body, and we sample that data at a certain rate, we filter that data in a certain way to clean it up, and then we have basically raw neuro or psychophysiological measures. But, and this is something I will talk about in more detail later, these data need to be translated into a representation of the state of the person. So we have a lot of raw psychophysiology. That psychophysiology is often quantified in a certain way. We will sometimes do something that we call artifact correction. What I mean by that is that we will look for where the signal is incorrect for some reason, or if physical movements interfere with the signal, and try and correct those things. And what you see here is that we take a lot of signals from the body in this case, and then we translate it into, this is an emotional model of the person. So then we have a representation of the state of the user. And then the second act of translation is if we can measure the user in real time, and if we can represent the emotional state of the user in real time, what do we do with that information? We can translate it into an adaptive controller, and it is the adaptive controller that controls how the data from the state of the person is translated into adaptation at the interface. But what we're going to be talking about today mainly are heuristic rules that we would use as part of the adaptive controller. So if the user is very frustrated, then we may offer help, for example. If the player of the game is very bored, then we increase the difficulty of the game. So the adaptive controller is a thing that translates the state of the person into actions at the interface. But there is a whole design process that is going on there. Now, the reason the biocybernetic loop is so important, I think, is because it acts as what I call a unifying metaphor or structure. There are lots of different things going on within a loop. We're collecting data from the person, we're doing live data analysis, we're translating live data analysis into actions at the interface. So the loop is a thing that holds the whole structure together. What the loop also does, certainly in the adaptive controller, is that it describes the purpose of the system. The system is designed to do something, to make the game more interesting, to stop people getting angry, to detect whether someone's too sleepy to drive the vehicle. And so what the loop does in the adaptive controller is it describes what the system is designed to do, what the purpose of the loop is. As you might imagine, and as you're going to see later on, there is a whole data processing pipeline associated with these types of systems, by which we take raw data, we translate it into some kind of representation of state, and then we translate that state into actions at the interface. And so what the loop does, it encapsulates that data processing pipeline from the beginning to the end. And what it also does is that it connects the active classification, by which I mean we say, when we classify someone into a state of, say, high stress or low stress, to adaptation at the interface. So the interface has got to adapt in a way that is appropriate, but the way it can adapt is limited by the way that we classify different states. So let me take one of those things, first of all, one of those translations, first of all. I'm going to talk first of all about this first part of the loop, where we quantify states from the person. So I am a psychologist by training. So this is a kind of bit that I am in some ways more familiar with, because this is what psychologists do all the time. We take measures and we make inferences about people's behaviour and people's states. So what kinds of states are these systems trying to detect most of the time? Well, a range of different things, really. There's a lot of emphasis on emotional states and things like stress and anger and anxiety. We can measure things that are negative emotional states that are linked to mental health issues. There's a lot of work on cognitive workload, and there's a lot of work particularly on detecting whether someone has too much to think about at one time, what we call overload. And there are also other states that we may want to recognise, such as whether someone's too bored or too sleepy, and that means that they're unsafe to operate machinery. And one thing, a technological trend that is driving this sort of system is the explosion in wearable sensors. So where lots and lots of wearable sensors are now hitting the marketplace. From these kind of head-mounted displays here, which are all measuring brain activity, to the kind of smartwatches and activity monitors that you can be familiar with. We also have the ability now to detect things like heart rate from a webcam. And there's even the next generation, such as these like things where you have temporary tattoos on the skin that can measure biological signals. So the explosion in wearable sensors means two things. It means that their signal quality is getting better. It means that we can take these measures out of the laboratory and use them in the field, which is what you want to do with these sorts of systems. And it means that a greater range of measures are becoming available to us. Now, obviously, sensors that measure the brain and the body do not stand alone. There are a whole range of other sensors. We have sensors that do facial recognition, that measure emotional states, sensors that measure the activity of the person, and obviously we can measure things like GPS using a smartphone. And that's important as well, I think, because when you measure physiological activity, particularly in the field where people are going doing everyday life, it is important to know what else is going on with the person, to have what we call multimodal representation of the person, which means that we take measures from the brain and the body, and we also take measures from other places as well. Now, the type of data that I'm talking about has several characteristics which makes it potentially very powerful. If we record data from the brain and the body, that data is continuously available. It is passive in the sense that the person does not need to do anything. The person can just sit there, as you're sitting there now, and we can record data from it. The data is quantitative and it is objective. And perhaps more importantly, when you record this type of data, you can measure conscious changes in a person's psychology, and you can measure unconscious changes as well. So you can measure things going on with the person that they may not be aware of consciously. And that makes it very powerful, because if you put a sensor on someone, then this data is streaming from the person all the time, and you can just take it and translate it. But of course, life is not that simple. What we have that makes things very complicated is this act of what we call psychophysiological inference. So we have basically a bunch of physiological measures on this side. So this is EEG and ERP, which are from the brain. ECG is heart rate, BP is blood pressure, respiration. GSR, or skin conductance level, is measure of sympathetic activity. And EMG is the activity of the muscles. So you have lots of different measures that you can use. And what we then have to do is translate those different measures into cognitive state of the person, or the motivational state of the person. Are they trying hard or not? Or whether they are happy or sad. Now, it would be wonderful if the relationship between these measures was what we call a one-to-one relationship. So that whenever you measure EEG, it always gives you cognition and nothing else. And often, certainly in some research that I see, people tend to treat these measures as kind of plug and play in a way. And they assume that if you're taking this measure, then you must be getting this aspect of the user psychology. The reality is more complicated. The reality is that you have what we call a many-to-many mapping. So that measures, say a measure like EEG, will collect data about the cognition of the person. It will also collect data about the motivation of the person and the emotion of the person. And, sorry. And what that means is that if you are trying to infer the state of the person based on different measures, then that is problematic. Because the links, you've got lots of different links going on. So, and it's problematic because these measures are really, really sensitive. They work very, very well. But what we really need to do, I think, is to take the measures in the field, but combine them with other measures in order to give us a context of the measures. So psychophysiological measures and neurophysiological measures are very sensitive, but terribly, terribly sensitive to context. And that's what makes interpretation quite challenging. Now earlier I showed a slide where I said these are the sensors that we take from the brain and the body, and these are other sensors that we can take as well. And my suggestion is that we can combine sensors from the behaviour of the person, their activity level, and other things that are going on with them, with these more sensitive psychophysiological measures to establish what is going on with the person. Let me give you an example of what I'm talking about. This is from a recent project that we did in Liverpool, where we were asked to measure how people get angry when they drive to work. Okay, so what you're seeing here is a kind of Google Map representation of, I guess, someone's anger levels. And what we're doing is measuring the cardiovascular activity of the driver as they're driving into Liverpool. So Liverpool is here, So this is the beginning of the journey and that is the end of the journey. And what we've done in this case is really, really simple. We've measured the heart rate of the person, and we have, obviously you get a normal distribution, and so where the faces are green, that means low heart rate for the person. So the person's relaxed at those points. The yellows are everything around the average, and the red faces, of course, is when heart rate is high. And what we did was we measured cardiovascular activity when people are driving into work, and we combined that with measuring, taking a camera, a picture of what is going on in front of the car, and measuring the speed of the vehicle as well. And if we put those pieces of data together, you see in this particular case, you see we've got a green face there? Well, we've got a green face, the driver's quite happy because they're driving at 40 miles an hour, which is about as fast as you can go on that type of road, and there are no cars in front of them at all. So, if we put the measures together, we can understand why the heart rate is low. Similarly, if we look at the red faces towards the end of the drive, you can see that speed is lower in this particular case, and that they're stuck at traffic lights at those particular points. So we're confident to say the rising heart rate happened for that driver there because they were frustrated that they could not get into work on time. And I present this to you just as a very simple example of how you can take data about the context of the data capture with the physiology data itself and put them together to make an interpretation. So what we basically do when we make this quantification is that we make a dynamic representation of what I call the digital self, a digital representation of the person. The measures are sensitive but difficult to interpret. So if we can measure context as well, then that boosts the validity of the type of inferences that we want to make. It allows us to say something about which specific stimuli are causing something to happen. And what we have in the end is what I call multimodal data. So representing the user by taking data from lots of different sources and combining them to get sensitivity and context. Okay, so does everybody follow me so far? Is that clear to everybody? Okay, good. Now the next bits of the loop that I'd like to describe is this aspect of intelligent adaptation. Now this is philosophically, this is a different way of interacting with computers to what we're used to doing. So we have this adaptive controller that is taking this data, and then things are happening at the interface because of the relationship between the data and the adaptive controller. Just as a basic background, this is the way I would like you to think about it. And this is not my idea, by the way. This is a guy called Lawrence Hettinger wrote this in the end of the 90s, I think. So Hettinger and other people have argued that the way in which we communicate with our computers at the moment is what they call asymmetrical human-computer interaction. And what they mean is, as a user, I can interrogate lots of different things about my computer. I know how good the Wi-Fi signal is, how much battery power it is, what peripherals are connected. I know lots about my computer. But my computer knows nothing about me. The computer is blind to the person's actual context. And so what we're arguing, and I guess physiological computing and the loops that we're going to talk about today are an example of this, is that we want to aim towards a symmetrical sort of HCI, where the user has an idea of what is going on with the system, and the system understands what is going on with the user. And so what we basically have there is a genuine dialogue between two things. So, you know, whether that is a good thing or a bad thing remains to be seen. So if we have this situation where the user is generating a model, the system is generating a model of the user, and the user has a model of the system as well, then, you know, feedback becomes kind of quite important. So if we have someone in a biocybernetic loop, we're collecting data from them, and then we have feedback at the interface which says you are happy, you are sad, you are tired, or whatever, then we have two things. We have the machine perception of the state of the user, but also we have self-perception of the state. We know how we feel most of the time, right? So if we can, and so we have these two different things going on. So the system makes an assessment of the state of the user, and the user, we have a process in the body called interoception, which is a way in which we assess emotions and fatigue and all kinds of different things. That gives us our self-perception of the state. So the problem, if you're designing an interface, is how to develop a biocybernetic loop which gives feedback to the person, but appears to be accurate and earns the trust of the person. And this can be quite challenging. If you think about it, imagine we have a system that detects 3 states from a person, whether they are happy, whether they are neutral, or whether they are sad. So we have the computerized assessment of the state that the system makes, and we have the user's own experience of their own state. Now, if the system says they're happy and they feel happy, then that is okay. But if the system says that you're in a neutral state, but you actually feel quite good and quite happy, you think, oh, it missed that. That should have been recognized. But if the system tells you that you're sad when you actually feel happy, then that is bad. That is something that gives you, that may shake your confidence in the system. Similarly, you know, if you're feeling okay and the system tells you that you're happy, you think, no, I'm not. Or the system tells you that you're sad, then you're confused by that as well, and so on. So as you can see, we've got various points of agreement and disagreement between the state of the person and the state of the computer, and the way the computer perceives the person. And at the moment, we know very, very little about this relationship. Not very much work has been done on what happens if you tell a person how they're feeling or what they're thinking, and if they agree with it or disagree with it. Now, a few years ago, we did some work at Liverpool to explore this issue. And the system that we had was kind of quite simple in a way. We had people watch a series of movie trailers. And while they were watching the movie trailers, we recorded data from the EEG, that's the electrical activity of the brain, and from the heart rate and from the skin conductance as well. And we had developed like an algorithm, I guess, that said if the person is interested in something, then they find it attractive, they're activated by it, and they understand it. So we were trying to measure interest in real time using these range of different measures. And we measured interest as a binary state, either low interest or high interest. And what we did in this particular experiment was that we provided feedback to the user about what was going on. Now this experiment, the way it was designed, is that it had 2 stages. If any of you are familiar with machine learning, you'll understand why this is. We have a training phase for the machine learning, and then we have a testing phase for the machine learning. So in the training phase, the person watches a movie and they say, this is high or low for me, and they give a subjective rating. Now, once we had 2 examples of a high interest movie clip and 2 examples of a low interest movie clip, we then generated a machine learning algorithm, a support vector machine, to be precise. And then from that point onwards, they would watch the movie, they would provide a rating of whether they thought it was high or low interest, and then the system would say, the system thought this, that it was high or low interest, and they could say whether they agreed or they disagreed with the assessment of the system. And the way that we did it, so we had this training phase, and we did an initial build of the support vector machine, and then we showed them, I think, we had a testing phase where every 10 movie trailers or so, we stopped and we rebuilt the classifier. So they watched 30 movie trailers in total, and at the 10th and the 20th, we stopped and did a rebuild of the system. So, if you're unfamiliar with machine learning, the reason we do this is that the support vector machine that is making this classification of high or low interest should not be so good at build 1 because it doesn't have very much data, and then it should be much better at build 2 and even better at build 3, yeah.
Did they rate during the 10 and 10 as well as
yes.
the first?
Yeah, so they were doing those ratings, so we had ground truth to use afterwards, yeah. But the important thing was that they did the rating and the system said, we thought low interest. And so they got that feedback after they'd done the subjective rating. Now, so if we look at this in terms of what I call mathematical accuracy, or the system's estimate of its own accuracy, we get a chart that looks like this. So it starts off at about 82%, and by build 3, it's up to 90%. So that's roughly what we sort of expected, is that the system will get better over time. And for those of you who are interested, this is the F1 score, which is a measure that's used of mathematical accuracy of classification. Then we compared that with how people assessed the made an assessment. So what you see here at the green bars is a subjective assessment of how accurate the system was. And what we see is that subjectively, people put accuracy around 10%-ish lower than mathematical accuracy, but it shows the same trend. It gets better over time for the person, so they are at least in synchrony in that sense. And the important thing to understand here is that often in effective computing type applications, people are really looking at the mathematical accuracy. We don't really know how it interacts with the person's perception. The other thing that's interesting is that we looked at the correlation between the two, between the mathematical accuracy and subjective accuracy. At build 1, there is very little correlation, but the correlation between the two rises significantly as we get to build 2 or build 3. There's one of two different interpretations here. Either the system is genuinely getting better, and as it gets more data, it is able to more accurately approximate the user's own perception of what is going on. The second interpretation, because this was quite a long experiment, is that by continually exposing the person to feedback from the system, it starts to entrain the user in effect. The user then starts to change their perceptions in order to bring it in alignment with the system. So that's another interpretation. So I basically present this to you as an example of understanding how feedback from the system interacts with the person's own understanding of their own state and what is going on. The other important point that needs to be made about this sort of system that we're talking about is that it is what I call a machine with an agenda. The loop is designed to make something happen. In that particular case, the loop was designed in order to recognise when a movie trailer provoked high interest, and then what it could do later on is basically select a subset of high interest movie trailers that work for you. So the machine is trying to do something to the person. It may be trying to make them less frustrated. It may be trying, as you'll see later on, to get them to exercise more or move more. But what is going on with this symmetrical human-computer interaction is that as users, we are giving up control to the system. The system is taking control away from us as users. And so we have to be very careful about what the agenda is of the system, because you hope the agenda of the system is the same as your agenda as a user. But this may not always happen. It depends. Let us look a little bit more about machines with an agenda and what they can do, and I'm going to use gaming as an example of this. Now imagine we have a game which is taking signals from the brain and the body, and what it is trying to do is to make a better gaming experience for the person. My old colleague Carol Gillies wrote a paper some years ago now about a game, physiological computing game, that could do one of three things. It could either challenge somebody in a game, it can help the player in the game, or it can enhance the emotional experience of the player. And these pictures are from a photography project that I guided in the States, where we have people playing games and had a camera on them. So they're like genuine gamers. And if you play games yourself, you know that people get very excited and so on. But can we make games even more engaging by using this kind of machine with an agenda approach? Let's imagine you have a first-person shooter game. And imagine that you've got different ways in which you can challenge the person, you can help them, or you can make their emotional reaction stronger. We can do it in quite an explicit way. So if the person is bored and needs to be more challenged, we give them more enemies to fight. If the user requires help, is stuck in the game or so on, you can help them in a very explicit way also by having an avatar pop up on the screen that gives them a hint or advice about what to do. If we want to explicitly manipulate their emotions, you could have them interact with an avatar in the game who's very emotionally expressive, who's shouting, and very excitable and so on. So these are all ways of adapting the interface in order to enhance challenge or help the person out or give the person more emotional experience. The other way of doing it is doing it in a more subtle way, a more implicit way. So if you want to challenge somebody, rather than giving them more enemies to shoot, we increase the AI of the enemy. Now that's something you would only notice in the game with some practice and if you were really looking for it. Rather than helping them by having an avatar pop up and say, why don't you do this, you could leave more resources that help them do the game, more ammunition or health or whatever. You just increase the number of those things lying around in the game. And that helps people if they're starting to struggle. And if you want to enhance or change the emotional experience, certainly in something like a game, a first-person shooter, you can change the way the game looks, the darkness, the lighting, the music that is played. These are all things that you can manipulate in order to give people a different emotional response. So what I'm arguing is that if you have a game that has different agendas that can be going on simultaneously, we can do it in a way that the person notices, or we can do it in a way that the person may not notice so much. Now if we have an explicit adaptation, so the system's doing something that's quite overt at the interface, the person notices this. And this is good because it's a very effective and strong way to influence a user state. The downside of it, if you think about the slide I showed before with the smiley faces on, is that if it gets it wrong, the person notices. So you can do these things in a strong way, but if you do that and it gets it wrong, then you tend to produce quite a high level of false alarms. And that could be a problem. So what we have really is an explicit adaptation that I feel should only be used conservatively. You don't use this very often because there's a strong chance you could get it wrong. If you do a more implicit adaptation, which is covert and less likely to be noticed by the user, then in some ways that is weaker. It is a more subtle way and it's a less effective way to influence the user state. But if it gets it wrong, the user is unlikely to notice. So you can use that more liberally in a way. So you can manipulate things like the music in subtle ways and the lighting, and people will probably not notice that much even if it gets it wrong. So what I'm suggesting, I guess, in a way, is that if you want to change the state of the user, if you want the machine to have an agenda in this kind of way, then you can do lots of covert, implicit adaptations, and if you're really sure you know what's going on, then use the explicit adaptations. And what I'm trying to get you to think about really is how the interface works and how the person interacts with the system. Now, going back to this idea of the machine with an agenda, a machine's got an agenda, and what's important here is that the machine, for example, might just want to give you a better gaming experience. But as you've already seen, it's got several different ways of doing that. So how does it do that? A little later on this morning, I'm going to be talking about a case study where we made an adaptive version of Tetris. So staying with going to Tetris at the moment. Now we chose Tetris because we think it's a very simple game. But if you think about it, Tetris can be kind of quite complicated if you're designing adaptations for it. So if we wanted to make a version of Tetris and make it harder for you, we could do lots of different things. We could increase the drop speed, which is actually what we did, so the shapes drop down faster. We can reduce the vertical space so you don't have as much time to respond. We could select shapes that don't fit with the board. In order to stimulate people, we can increase the volume of the music, we can increase the tempo of the music. We could drop two shapes together. We could only eliminate the rows when you've got 3 rows completed at any one time. Only eliminate rows when the blocks are all one colour. You can introduce more than one board. So these are all ways of making Tetris harder that you can do. When you have a system that can adapt, I've used this phrase functional vocabulary, and what I mean by that is that it's got lots of different ways in order to achieve its goal, in order to achieve its agenda. Now, what I'd like to do now is to ask you to think about the implications of that and how it works if you have, if we're able to extend the way in which the system interacts with the person over time. Now, imagine we've got a system that, let's say it's a game, for example, that detects frustration. And if the player is frustrated, it tries to help them to do something about that. So imagine we've got a situation where the person is playing the game and they get angry. during the game. System detects that they've got angry, and then it looks at its functional vocabulary, and it can do a number of different things to help an angry player. It could reduce the difficulty of the game, it could offer help, it could try and make the music calm down to get them to calm down a little bit, or it can suggest that they take a rest break and leave the game alone for a bit and then go back to it. So in this first phase of adaptation, in this particular case the system decides to suggest a rest break. So it switches the game off, puts up a coffee cup icon and says, take a break now, and then what happens next? Well, in this particular case, the user is still angry. So what I'm suggesting is that the system knows at this point that it's made an adaptive selection and that did not work at all. So then it has to do a second round of adaptation. So it says, okay, the person's still angry, let us see what is left. We can't look at a rest break anymore, so let us try something else. So then it offers help to the person, and that makes the person happy. And so that adaptation works. And I guess what I'm trying to get you to think about is if a system can monitor the person's responses in real time, and this is a little meta, but the system can also assess the effects of its own actions on the user as well, and take that into account. So a biocybernetic loop, in effect, is a self-monitoring loop. And if the loop can achieve different things using different adaptations from the functional vocabulary, it can also monitor the effect of each adaptation on the user by looking at the dynamic representation of the user. It can check that against expected outcomes, but what it can also do is it can keep a record of what worked for that particular player. So what we move towards now is something which is a system which delivers an implicit form of personalisation that is able to look at the different ways in which you can get things done and pick the right one for that particular person. And let us think, obviously these systems don't exist yet, but let us imagine they do, and imagine how that works over time. So what I suggest is that when a person sits down with one of these systems for the first time, the first few minutes of use, the system is essentially improvising. It does not know what the user really wants. And so what it does is it makes a series of generic adaptations. And then as the user continues to use the system over the next few hours and days, then it begins to generate a model of which adaptations, which interventions work best for that person. And so we have the second stage, which might take place over several different days, which are called reciprocal coupling. And all that means is that the system can now adapt in a personalised way to the person, based on the recent history and based on the consistency of the user response. So what we have now is a system that is building a representation of the user that is, in psychology we represent the states of the user in two ways. We represent user traits, which are stable over time, and user states, which are variable over time. So now you start to recognise the traits of the person as well as the states that we're working on. And if we have a system that person uses over a long time, a series of years, then we have a highly personalised system where we've built a probabilistic model of adaptive strategies, which adaptive strategies have the best chance of working for that person, and we have a very, very detailed profile of the person, a real digital self, which represents the traits of the person and the states of the person as well. Obviously, in order for this system to work over such a long period of time, the functional vocabulary of the system needs to be very large. It needs to have a lot of freedom to play with. And we're not there yet. But what I'm suggesting is that this type of adaptation over time takes us into the area of human-computer co-evolution. It takes us into an area where you have like software for life and those types of ideas. So when I'm talking about intelligent adaptation, about translating, what I'm talking about is translating an agenda into adaptation at the interface. And again, this is really important. The agenda must be acceptable to the user in the first place. And there's a whole host of ethical issues around how that's going to work. We have a series of different design options. We can make the system give explicit feedback at the interface. We can do things that are more subtle that the user may not notice. And we may be able to, if we move to second order monitoring of the person and a self-monitoring loop, be able to create systems which co-evolve and develop with the user. So that's a kind of futuristic take on where these systems may go at some point over the next 10, 15 years or so. So that's my introduction. If anyone of you are interested in the work that I've talked about, you can find all the papers on this website. And